Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're hopefully going to spend this hour talking about ontologies and understanding and formulating semantics for software. And I want to thank Jane for opening this session with a talk about building software ontologies. Thanks, Jane.
Thank you. I realize I'm the lucky person that got the last speaking spot of the day, so I'll do my best not to send Sol to sleep with yawning already. Okay, so what I was charged with is really just to talk a little bit about my research, and what I'm really going to do is try and show you some of the areas that I think NLP, that we're trying to use NLP. So I'm sure the NLP people, I hope you're going to come and tell me, well, you should try this, and it would be better to do that. But I think this is going to kind of provide a different kind of view of software engineering and look at a couple of different problems, and I'm going to talk about the kind of things that we've done. We've seen this kind of slide 3 times now. This is the 3rd time. Tao showed us kind of like the project artifacts, and Earl showed them to us. So I won't spend much time, except to say that this is the context in which we're working. So there's lots of different software artifacts. And my interest lies in making connections across these. So some of the things people have talked about really focus on one kind of artifact, which is source code. And the kind of world we live in is trying to make connections across all of these different kind of artifacts. So to query across them or to trace across them. And actually, traceability is very, very similar to project-wide querying, because what we're trying to do is make connections between things. So a couple of quick examples of what the kind of thing we're interested in, kind of compliance questions or safety analysis questions. Traceability is really important in the world of safety critical software. So in safety critical software, you're going to start off with regulatory codes or hazard analysis, fault tree analysis, those kinds of things. And you need to be able to make the connections all the way down to the code and the test cases to show that your software is compliant or that it is safe for use. We've already had lots of people talk about things like fault prediction. Bug triaging is another one of these things. We have these different kinds of software artifacts, and we're interested in allowing people to make queries across them. And one of the things that we can see is that there are many different project stakeholders. They're all going to have different kinds of queries or questions they want to ask that will support their particular software engineering tasks. And they're all going to ask their questions using their own terminology in their own ways. And that's really what we want to address. In fact, I visited, have a couple of industry collaborators, and actually about 8 years ago, I went to one particular collaborator, and they told me because of process improvement initiatives in their companies, they had to have traceability in place. So they spent a lot of time establishing traceability, but they never actually used their trace links after they created them. So I wanted to know why, and it's one of the reasons is the barrier of actually formulating queries that are actually quite complex using SQL or something like that. So one of the things we wanted to do is to create this natural language interface for querying software projects. So why this differs from, I think, kind of some of the other database natural language interfaces for databases is that as well as kind of querying the actual data in the database, we want to be able to ask software engineering type queries. So it's like makes it very domain specific. For example, are there any hazards with no identified contributing faults? We'd like our users to be able to answer those kind of questions. Or list all requirements related to heat sensor faults. So these are the kind of things, and I'll show you a couple more examples in a minute. So what we do is we basically present the users with a database schema, which we call a traceability information model, and it captures all of the different software artifacts that are available for them to query against. What I'm not even going to slightly touch on today is the fact that this data is not sitting nicely in some relational database. So I'm just going to pretend it is there today, but there's a whole bunch of engineering that has to go on in order to actually dynamically in real time collect the data from third-party case tools, maybe distributed internationally, and all those things. So for now, we'll just assume, which is an incorrect assumption, that the data is all here.
So if it's not in the database, why are you using SQL exactly?
We currently use, we have some other intermediate formats, but we currently use SQL just as an intermediate format. And we've also done some work in going from that into kind of case tools and things like that. So it's not the end. It's not the end at all. My collaborator happens to be a database person, so it was a convenient kind of place for us to focus on the upfront NL. So, yes?
If I can just stop, are you later going to talk about how this kind of data is collected?
I can, but it's not the focus of what I was planning on talking about today. It's another whole kind of challenge, but I can answer that later. So just to say that there's different kinds of queries. This is one example of a query that somebody could ask. And if you look at it, they're just really asking for data that exists, that's a natural byproduct of the software engineering lifecycle to be retrieved. So all we have to do is take that, map it onto these different artifacts, find a path that connects through them, generate our SQL query for now, and return results. A second kind of query, which really builds a lot on what Tao was saying the other day, is much more analytical in nature. So here's this query. It says, who is the best person to check the fault-prone classes in components related to temperature controls? There's actually 3 analytical functions embedded in that one simple query. We have a recommender system, which would have to answer who is the expert. We have a fault prediction predictor that can identify fault-prone classes. And then we have some kind of, maybe semantic analysis that will kind of look for things that are related to temperature controls. So this is an example of the kind of analytic query that we're working towards Tiki being able to answer. So right now, Tiki, we just take the query. As I've learned, we're using the old-fashioned approach, but we use some kind of heuristics to map. Well, first of all, we pre-process, we tokenize, we map onto the different artifacts. So currently we use a heuristic approach to do this. We're then using some machine learning in the middle that we're just working on right now, where we basically train Tiki to disambiguate when there's ambiguous mappings. But we don't have one big kind of statistical, machine interpretation going on now. It's like heuristic with the benefit of some classification. So that's this area of Tiki, natural language interfaces. And our goal here is to allow people to ask these queries against the software engineering projects. This turns out to be, a very special, so traceability, which Earl has given us a really nice introduction to, so I'm not going to bother with that. Thank you. So it turns out that traceability is a very special case of a query, because instead of the user coming along and telling what they want, we basically have a query which is made up of one software artifact, and then we're searching against something else. So the query could be a requirement, and we could be searching against source code. Or the query could be a regulatory code, and we're trying to search against requirements. And that's the example that I'm going to show you. And I'm going to show you some of the NLP things that we've been trying to work on to solve this. Whoops, I'm jumping to. So these are examples of tools that use basic information retrieval and try to match things up. And this has been work. I think Andy's probably going to talk a little bit more about information retrieval methods tomorrow. But these are things that our community as a whole have been working on for at least a decade or more. I mentioned in my kind of introduction that one of the things we started thinking about 2 or 3 years ago is if you look at those information retrieval methods, we can trace from requirements to code or all these different kinds of things. We usually only achieve, at the best, about 90% recall. And precision that's kind of around 20% or something like that. So that's kind of on a good day. And I should say one reason for that is because we're doing search in a very small closed space. I think Dawn or someone had mentioned that we don't have the benefit of many people before issuing similar kind of queries. So some of the things that you can do in a much larger search space are not available to us. Nevertheless, we realize that humans are able to generate quite accurate trace links. And so we asked ourselves this question: what goes through a domain expert's mind as he or she performs the tracing task? And that was the beginning of our journey into natural language processing. So here's an example. Here is a regulatory code, and then here is a requirement, and we want to know, are these two things related to each other? And if we'd used ordinary information retrieval, then we possibly might have created a link between them, but we also would have got a lot of other links that were not related because of some of the kind of less important words there. So we asked ourselves this question, and we found that the domain expert will be able to reason about the concepts in the domain. He knows, what acronyms stand for. He knows when words are similar have similar meanings. He knows what, what is part of other things. So an automobile controller is part of an automobile. And he can reason, or she can reason about all of these things and determine if a trace link exists. So this was our quest to build this kind of much more intelligent traceability system that would be able to return highly accurate trace links. I don't really have time to go into our whole process, but we basically built it around this notion of action frames, which I'm sure the NLP people are kind of familiar with. And we take the artifacts, we parse them, we represent them in this intermediate structure. So an action frame contains a verb, semantic type, thematic roles. We assign each verb to both a syntactic group and a semantic group. We use the syntactic groups in order to identify and extract the action frames. And then we use the semantic groups alongside a set of heuristics which we've identified to reason about when the occurrence of an action frame in a source artifact and a target artifact means that those things should be linked together. Currently, our model is a little simplistic because it looks only at single pairs, and we know we can improve it if we look at sets of action frames that occur in source and target artifacts. So this is an example. I took out the animation because it takes too long to go through, but you can see here we have one action frame. Here's another one. Here the verb belongs to the receptive group, and in the second one the verb belongs to the transmissive group. So we have sets of heuristics. Here are the heuristics for this specific receptive-transmissive pair. And we compare, we go through the heuristics, and if all of the heuristics pass, then we declare that a link exists. So what we found is that, whoops, I'm going to bring this up. These are the results that we were able to obtain using our domain-centric expert traceability system in comparison to the vector space model. So you can see that we were able to achieve much, much more accurate traceability. But there's some problems. The first problem is that one of the things that I didn't mention is we rely on the underlying presence of ontology. So we have to be able to reason about things like similar meanings between two different concepts. And one of the challenges here, so we need ontology for this to work for a very specific domain. And some of the ontology is just related to software engineering in general, but a lot of it is very, very domain specific. And a lot of the domains that we're working in are highly technical. So you can't just go out and find ontology that you could reuse. So for example, this data set here is actually from the domain of positive train control. And if you go and look at, for example, some reviewers for papers said, why don't you go and use the transportation ontology? And it's completely not suited to our domain, which has highly technical terms in it. So for this to work, we've basically just created a new problem, which is that of ontology learning. And once we've learned the ontology, we don't know yet if the heuristics that we've learned can be applied across different domains. We have some evidence to show that many of them can be applied that we've learned them on one domain and we can apply them on other domains. But I want to just use a little bit of my time now to talk about what we've done to learn ontology. And I think that, Tanya, I think this is an example of, we think there's something a little bit unique about what we're doing from an NLP perspective, but you guys can tell me if I'm right or wrong. Okay, so our approach for learning domain ontology, first of all, we have domain documents, and then we have project artifacts. And then we use a variety of different extraction methods. So I'll talk about these in a minute, but I think they're pretty standard methods that people use for ontology building. And then a secret weapon is traceability links. Because when we started to think about it, we thought if you have trace links for a specific domain, then you know that there is some concept in the source artifact and some concept that's in the target artifact that are related, because somebody has said these two artifacts are related. And if we, given our existing ontology, our existing knowledge base, if we cannot explain the link, then we have a really good hint that we could go and search for a relationship between a pair of concepts. So of course there might be many concepts in the source artifact, maybe 4 or 5 different noun phrases or something like that, and the same in the target. So our approach really seeks out the knowledge that would fill in that gap. So we think this kind of really creates a semi-supervised way of learning because we now have a hint about something that exists. Okay, and then we use these methods, which I'll talk about in a second. We create a profile of candidate facts. We've used machine learning here so that given all of the information that is we get from the lexicosyntactic patterns, association rule mining, topic modeling, and semantic relatedness, which comes from WordNet, we try to train this to evaluate which of these facts are likely to be the ones that cause that trace link to occur in the first place. Yes?
That corner, the trace matrix, if you take it out of your approach, what's the compromise of the overall approach?
It's less guided because now what this does is it tells us that given this pair, maybe this regulatory code and this requirement, that there's some concept, some pair of concepts in there that are related and should be put into our ontology. So it means that we can focus our search efforts to find the concept that actually is the one that's related. As opposed to, for example, if you were to just use lexicosyntactic pattern extraction, you can search through all the domain documents, but this kind of creates more of a guided environment for it. Yes?
Does it sort of mean that the source and the target have kind of their own latent ontologies, and what you're doing with the trace matrix is basically aligning them?
It could, but they probably share a lot of they probably share a lot of facts. Because I know when we started this, we saw that there's 2 different kind of ways of thinking about this. One is the kind of the 2 parallel kind of ontologies that you look for the connections, and then the other is you just build the blended one, and that's the approach we've taken. One of the reasons we've taken that is because of the problem that we found in kind of overlap. So I'm going to focus on PTC, which is a positive train control. We were given... yes?
Could you say just a few words? How structured is your ontology? Exactly what you're aiming at? I mean, how many layers? What just to understand what you call ontology.
I'll show you I'll skip a couple here and show you a picture of it. Sorry, going forward here. So this is a really, really little bit of it. But basically what we're interested in is facts, kind of relations between facts. We're not, we only have a certain amount of knowledge right now about the relationship that occurs between these facts.
Is A and part, right? The main 2 main.
Right now we do, but obviously, yeah, with the lexicosyntactic patterns, if we can find patterns that way, then we have the opportunity to label these. But kind of skipping back a little bit, we basically put the human in the loop and allow them to label those. So this is not fully automated, but maybe Dana has good ideas for us coming along. Okay, so one of the problems we have here one of the problems we have here is, for example, with this positive train control, our industrial collaborators gave us 450 documents about positive train control. So that's quite a lot. They're quite lengthy. And we basically mined them for nouns and noun phrases, so we focused only on that. And then we did the same with a small subset of requirements and artifacts from the system. And you can see that there wasn't really much overlap. So a large percentage of the nouns and noun phrases that were found in the software artifacts were not in any of those 450 design documents. So basically unseen kind of concepts. That's one of the reasons that we think it's more effective to try and build, focus our effort on building ontology that's actually needed by the software artifacts and using the traceability matrix for that.
Like for the document you mentioned on your table, like how high percentage of them are confidential, like to the company or to the organization?
Yep. This one is completely confidential. These ones are not. So they're kind of much smaller. But we deliberately included them because they're ones that we can share with people. So the one that is the real world one is proprietary. It's always the case, right? We actually now have access to a really large data set from our Indian collaborators, for which we have to fly to Pune to go and work on it whenever we want to. You guys may think it's hard getting data sets, but if you actually need ones with requirements, something else, and trace links, it's even harder. So, okay, this was just basically the same thing that I've said before about leveraging the traceability data. We identify key terms. Right now, we're only working with nouns and noun phrases. Obviously, we can expand that. We use these different methods. So we have a number, these are just example patterns, have a number of lexicosyntactic patterns, but as the NLP people know this, if you do lexicosyntactic pattern mining, you get quite high precision but very low recall in terms of the facts that you want to find. So we had a number of problems with that. We also, so in order to try and improve our recall, we also used association rule mining and topic modeling. And basically, this gives us more of a clue about where the relationships might exist. So if we know some relationship exists between something in the source and something in the target, and we can't find it with our more accurate approach, then we kind of resort to something that just looks for associations. And then we also used WordNet to try and understand a little bit more about the semantic relatedness using synsets and things like that. As I said, we then built this profile, and we trained it to try and recognize correct facts from incorrect facts. For the NLP people, one of the things we've really had a problem with, and I'm sure this is easy for you, but is in figuring out what kind of phrases we should actually be putting into our ontology. So it's like the longer the phrase is, then obviously we're overtraining it, and everything works quite well, but only for the test sets that we're training it on. And so we think we have to, so we're trying right now to make our kind of phrases in the ontology more general, but we don't know really the right way to do that yet. As I said, we put the human in the middle. We think that ontology building, the human has to vet this and kind of evaluate it. And so we present them these facts, and we ask them to kind of add some information. This is just an example of a very little bit of the kind of facts that we've created. one of the things we found for traceability purposes, I'm not showing this here because my PhD student, Jin, is just literally finishing it up right now. But we found if we try and infer relationships across the kind of different relationships in the ontology, that we actually get worse results than if we look just at neighboring facts. So one of the problems from the traceability perspective is it seems to reduce precision if you kind of do too much reasoning. This is something that we just started working on right now, though. Okay, and ontology alone isn't enough. This is my last slide after this one, I think. Ontology alone isn't enough. I already showed you this slide. And this is just to say that reasoning over the ontology, for example here, OBM is part of the automobile segment, is part of it. And we have shown that we can improve the tracing results simply by using ontology. But we really need these heuristics. And one of our open challenges that we are challenged to work on, and I really think we can do it, I hope, is to learn the rules. So right now, the heuristic rules that we have established for relating two action frames based on the semantic groups, those rules were built manually. I had a linguist on my team for a couple of years. And we spend a lot of time building those rules, but we think that there's a way to structure them and to learn them. So we came up with this structure and got a little bit stuck. We used genetic algorithms to try and search through the search space to try and discover kind of like the rules, because this is a structural representation of the rules. But anyway, it turns out we had more possibilities than the number of nanoseconds in the universe. So we have to figure out a better way of learning this. We have some ideas, and if anybody has any suggestions for that, I would be very, very grateful. So that's anyway what we've been trying to do in this area. And I think this is just a summary, so I kind of covered it. So yeah, it's just some of the recent papers we've done in this area. And this is my PhD student, Jin Gu, who's doing this for her PhD topic right now. So, yeah.
My question is, did you have a computational linguist on the team? The linguist, but a computational linguist?
No, not yet. So this is an example of, a lot of software engineers are kind of homegrown NLP people, and we just learn. I was telling some people, basically we go and look for the algorithms, but we don't know necessarily that we have best of breed. Yeah.
So if you were to look into the future, and suppose we have ideal NLP tools, could you just give the audience your ideal list? What would you like to have, if possible? And then we could project it on what's available or what could be the new research directions, because that's exactly what we're looking for here. Looking forward, what could be improved or new methods developed to help to do what you, because this is extremely, extremely interesting and challenging domain.
Yeah, it's been a really fun, cool domain to work in. I think definitely ontology, tools for ontology building. Because for software engineering, you're constantly changing domain. However, for example, our industrial collaborators that work in the area of positive train control, they build multiple systems in that domain. So it's worth the effort to build the ontology which can help them with their future tasks. So I would like, help, ideas, tools that would be useful for building ontology in specific domains, highly technical domains. And I realize this is really challenging, but we think we can give something to it as well by some of the kind of the semi-supervised learning, for example, from the traceability matrices. That's the biggest, most important thing. And then, maybe tools for helping us kind of learn rules, but I don't know if that's just a once-off specific thing. If we learn it one time, then it'll be good for every domain, or if it's something that would have to be redone for each domain. I don't know. think, yeah.
So I was trying to just follow up a little bit on Tanya's question, and one thing that would be really helpful for me, and maybe this conversation we can have in more detail later, but what's the criterion for being a node in the ontology? I think I understood the links a little bit better, and sort of, how do we sort of get to the next, kind of, does that just not align well with, things that you can get out of NLP tools? Or I saw you were using speech taggers, but I didn't know the full suite of exactly how it went, and so like more details there. I would love to hear about that.
So I would love to talk to you about that too, because I think this is something we didn't know the right way to do it. And so the first ontology we built had really long phrases in it, which is obviously not the right way to go. And it optimized for our data set to support traceability. So I think that's something we don't know the answer to that. So in the end, we can build an ontology that has simple phrases in it, but in the end, that might be for us like using only WordNet to identify synonyms. And when we've used only WordNet for traceability purposes, then the precision of the trace links has gone down. Recall goes up, but precision goes so far down that in the end, it's a losing proposition. So for us, we think we need techniques and we need to know what we should be modeling, and for us, it's also a kind of chicken before the egg thing. So we're trying to build something, and then we hope we can start improving it. But we've already reduced the length of things that are in nodes. And I don't know. Right now, we have only nouns and noun phrases, but maybe there's other kinds of things that should go in there too. I'm not sure. I think there's one question.
So your ontology had a bit of a hierarchy. Did that matter at all? Like if you strip it out and just treat it relatively flat?
Yeah. In the end, based on our last week's results, which are not here, we're not even actually using the hierarchy or the distant relations. I don't know the right way to say that, but we're basically right now just using simple facts. Like A is related to B. And one thing I didn't mention, my PhD student, Jin, is also working on, we had a paper, short paper recently that generates rationales for links. So we have to, in order for that to work well, we have to know the type, we need to know something about the type of the relationship. But yeah, so right now, of course, we like the idea of the ontology, but as the results that we got from last week is just pairs of facts actually work quite well for us. But you can, of course, extract those from ontology anyway. Yeah.
So even for pairs of facts, you can look at simple relations, like you have something is a subclass or something is exactly one other thing, but you can look at more complicated relations, like the edge between those two artifacts can mean something about the type of interaction that they have, right? So is that something that will be helpful for you? I'm wondering if you at all looked at doing something like that.
We're at the very beginning of this. The first study we did was we built our ontology manually. We built our heuristics manually. It was like a proof of concept. If we have all this stuff in place, does it improve the task we're trying to do? The answer was a resounding yes. So now we've started on this ontology generation. And I strongly suspect that, so right now, Jin just told me last week that she got much better results by only looking at single facts. But I strongly suspect that if we understood the type, the relationship between them, then it would not be all or nothing. And there'll be some relationships that we would reason over and would be useful to us. And then maybe others like siblings are not necessarily as useful for what we're doing. Yes.
Thanks for a great talk. I guess I had a question that's not necessarily just for Jane, but for anybody, which is is NEL, for example, learning any facts about things like Android API or the Lucene API? If you went to NEL and said, NEL, what does a broadcast listener do? Will it tell me anything?
Yeah, I'm about to test it right now.
Okay.
I think Luke and I looked at one another kind of skeptically, but I don't know. It all depends on what's on the web, I guess.
Yeah, I suspect there'll be some things in there, but not probably everything that software engineering people will be interested in.
Okay.
I think that's where Jillian comes in.
Okay.
That's what he's going to do.
Okay,
Put all of these things in now.
So I mean, maybe that's related to your question. Like, we did some work, let's say, a couple years back, and we published in Using Security, 2013, basically finding this traceability for an app description functionalities and the permissions mobile app is requesting. So we got some initial result, and then after our work has been funded by NSF on further that work. That work actually opened up some interesting direction in the security community. Because in the past, I mean, in the security community, they use testing, program analysis for tackling security problems. No one actually thought about using natural language processing or text analytics for difficult security problems. And since then, quite some papers, I mean, have been published by other groups in the security top conferences in these couple of years. People are catching up, I mean, in that community, I mean, kind of in a very competitive way, like everyone rushing in this direction. It's a very interesting phenomenon. If any of you have interest in that direction, I mean, talk to me, and I'm happy to share more with you. Yeah, I think broadly that's also covers in the software engineering area. The app description you consider as a high-level functional requirement, right? And then the permission would be security requirements. So it's somewhat related to traceability issues. Yeah. More questions?
I wanted to add actually to what you were asking about NEL is that NEL learns relations on top of an input given ontology. And so if in this ontology there are no software concepts, NEL is not going to learn about software. And so I think that's where, to some extent, if those things are in the web, you know, at some point somebody will think of adding them to the ontology, but this is a human-initiated act. And if those things are not in the ontology given to NEL, it's not going to learn about them. And so, again, this is work that William's group and Tom Mitchell's group are thinking of doing right now.
All right, get with the program. I mean, who cares about baseball games, man? I want to know about code.
But for that, you need a good ontology to get to know. Exactly.
Nell thinks MVC is a programming language, so it's partially on fault.
Oh, it thinks MVC is a programming language?
Yeah.
That's not so bad.
Well, we asked a lot of, just for fun, when we were building Tiki, we asked Siri all the questions we asked Tiki. It was kind of fun. Of course, Tiki goes, "That's an interesting question," or gives a very generic answer.
Is anybody using OWL for any of this?
I don't know.
I think there's a paper from Easter. People use some ontology stuff for testing.
Testing L or using L for testing?
Mm-hmm.
It's like using L for testing or just testing L?
For test input generation.
Oh, okay.
Right.
So I built an ontology for telephony about 25 years ago. I don't think anybody uses it.
All right, thanks, Jane.
Right.